section.
Mhm.
Is it a scalar quantity?
That integration over omega.
Yes,
So that's
omega.
what I
Sorry.
wrote. This thing.
Yes.
No,
Yes.
no, no. It's not. Generally, it's not a scalar. Scalar is a special case of this. So it could be like a. We call it one form. In general, it's a P form. We call it. We'll see what does it mean. It's an infinitesimal quantity. Itself is infinitesimal. You should have asked back then. So do not stay silent. Ask when you have a question. Okay, Jaber.
Yes, fine. No problem.
Okay, so you don't have any questions so far?
No.
Okay, great. Then Bajaj, Ms. Bajaj.
Yeah, no questions.
So you understood everything, like so far what's going on, like two kind of basis.
Not everything, but yeah, kind of everything. But yeah, maybe when we'll move further, I'll understand the things more.
Okay.
Yeah. So the mathematical part, yeah, they are clear. Yeah.
Okay, great. Then Prashanto Chakraborty.
Yeah.
You understood everything, like without
Yeah.
any confusion.
Yeah.
Okay, Robin Roy.
Yes, now I have no question.
Okay, Sipatul. Okay, Sulaiman.
Yeah, I am trying to follow.
So do you have any questions so far?
Not now.
Not now. Great. Okay. Then Zubaida Karim Juthi. Zubaida Karim Juthi, you're muted yet. I think she's not here. Soed Imaduddin Shubho.
It's okay for me.
Okay, so you understand everything. Don't you have any question?
Not now.
Okay. Okay, great. Great. Okay, so now let's build up our intuition a little bit, because we have now a set of equations here. So as we can see that from the proof here, that EU dot EU is 1, then what's gonna be EV dot EV? What's gonna be that? And how many possible dot product can we produce here? So let's tabulate and let's talk about it. So EU dot EU. What is this? We saw it's already 1, right? Then EU, but there is EV. What's that?
0.
0. Then EU, but there is EW.
0, obviously.
0. Then EV, but there is EU. What's that?
0.
That's 0. Then EV dot EV.
1. Sorry. He will be in the superscript.
Yes, if V is on the superscript, then it's 1. But
yes,
it's on the downstairs, we do not know what it is. Okay.
Yes.
Then EV dot EW.
0.
0. Then EW dot EW, what's that?
1.
This is 1. Then EW dot
0.
Oh,
and 0.
I want to write in a symmetric way, so let's write it this. So this has to be 0. So EW dot EV I want to write
0.
0. Then EW dot
1.
W, this is 1. So if I write like U equals to x1 coordinate, V equals to x2 coordinate, and W equals to x3 coordinate, like that. And instead of EU, I write E1, and instead of EV, I write E2, and instead of EW, I write E3, like that. Also, instead of those gradients, I write E1, E2, and E3. I can write like that. Then, can you tell me what is this thing?
Kronecker delta.
I haven't even write this thing yet. Okay, E1 dot say E1. What's this?
1.
This is 1. E1 dot E3. What's this?
0.
0. So as you can see, like when these two things match, they are 1. When these two things do not match, they are 0. So we can generalize this concept to this thing.
We using Kronecker delta.
I dot EJ. That thing has to be IJ, delta IJ. So when I and J are same, it gives you 1. When I and J are not, it gives you 0.
Yes.
Okay, now we have found a way to figure out or actually build this AU, AV, and AW. So let me show you. So let's say you have A equals to AU, EU plus AV, AV, EV plus AW, EW. But you want to figure out how much your AU would be. So all you need to do is to take dot product with the corresponding other basis, like that is gradient of that. So take dot product with this, like A dot E upper U. That will give you AU EU dot E upper U plus AV. Sorry, it's not vector. AV EV dot EU plus AW EW dot EU. So what do you get from here?
Superscript U.
Yeah, this thing is 0, this thing is 0, right?
Yes.
Then, and this thing is 1. So you get this. So if you want to figure out one component, then you just do this. Take dot product with the other kind of basis. Okay, so now say you have a B which is written in terms of those gradient basis, the other kind of basis. So say it's written as like BU EU plus BV, sorry, it's not upper, it's lower, BV EV plus BW EW. We'll see an example in a moment. So you want to figure out, like if you take B dot say EW, what do you get?
BW.
BW.
Which one, lower or upper?
Lower.
Lower.
Lower one. Okay. Okay, so far we are seeing that in a pattern here. So if you have a vector A, and if you take a dot product with EI, then what do you get?
Then I
A
will
lower
get
I.
upper I.
A subscript I.
Yeah, upper I.
Is it upper or lower?
Oh, sorry.
Lower.
Subscript.
Lower.
Yes, if you dot product with lower thing, it will give you the lower one, AI. So see, here we taken dot product with lower one, it gives you the lower one. Again, if you have a B, then if you take like upper one, take dot product with upper one, it will give you B upper I.
Yes.
And so on. So So there are names to it. So the set of bases defined as this tangent thing, these are called tangent bases. And as you can see, they are actually, by definition, they are dual. So when a set of vector, they satisfy with this kind of relation with one set of vectors. So the second set is known as dual basis. So we call it the dual basis. So it's a standard theorem of linear algebra. If you have a set, okay, let's state it and then continue. So in linear algebra, it says if you have a set of n independent vectors, those are linearly independent, obviously. So say like UVW, say UVW, 3 vectors. You can always find a corresponding set that is x, y, z, such that those 3 things are dual to it. By dual means, like if you take one of those, like corresponding one, like the first one, it will give you 1, and the rest, like u dot y, will give you 0, and u dot z will give you 0. So basically, if they have this kind of relation, two set of vectors, those have this kind of relation, those are known as dual to each other. So one we have identified as tangent basis, and another, that's why we are another identifying as dual basis, or cotangent basis sometimes known as. So any vector we can write in terms of tangent basis and dual basis, right?
Yes.
Only their components would be different. So okay, let's have an example. Let's have an example. I think that will clear many things up. So say you have a definition like u equals to x plus y and v equals to y. 2-dimensional system. So if I want to draw u equals to constant line or v equals to constant line, what are those?
Just y-axis and the 45-degree with the x-axis.
No, it's not y-axis. V equals to constant equals to y equals to constant, and that are these.
Sorry.
Line. So these are basically v equals to constant curves, or we are u curves, right? V equals to constant curves, constant surfaces, I would say. Okay, and when x plus y equals to constant, what are those lines?
They're creating minus 45-degree.
Yes, these are
Yes.
parallel lines. Oh, oops.
Why minus 45 degree?
Yeah, because when you have like x plus y equals to c, then x equals to c minus y.
Oh. Yes.
So this is the diagram. So okay, as this is in 2-dimension, curves and surfaces are basically same. Both are 1-dimensional, right? Surfaces are 1-dimensional and curves are 1-dimensional as well. So v equals to constant surfaces are also u curves, right? V surfaces are u curves, let's say. And these lines, these are u surfaces where u equals to constant, right? But those are v curves. So we can find the corresponding inverse relation. What is x and what is y in terms of UV? This is obviously V. What is x?
It is U minus V.
It is U minus V, right?
Yes.
Okay. Now we can find our basis vectors like delta, like EU. Say EU. We want to write EU. What's that? That is delta R by delta U, right?
Yes.
What is that?
Delta by it's
R is equal to xi plus yj.
Yes. Then if you take derivative with respect to U, what do you get?
it's just UI.
Is UI or is just this, except? Okay, I'll do it explicitly. So I'm doing this delta delta U of U minus V, that is our x coordinate except plus y hat. Y is V, y hat. So if you take derivative with respect to U, this thing is vanished. This part is vanished as well. Only remaining part is this thing. So it will give you x hat. Is that clear to everyone?
Yeah.
Carl, is that clear? Pooja, is that clear?
Yes.
Yes.
Okay. So delta U by delta R, we have figured out those are nothing but x hats. So we already know that EU is supposed to be tangent to the U curves. Look, is it correct then? So this is our vectors. X hat. Is that correct then?
Yeah.
Yes, those are tangent to the U curves.
Yes.
These are the U curves, right?
Yeah.
Horizontal lines. Okay, great. So it's going well. So then EV, what would be that?
Minus x hat plus y hat.
Yeah, these matches too.
Minus x hat
Plus y hat.
plus y hat. Yes, minus x hat plus y hat. Which direction is that? This is this direction, right?
Yeah. The V curves.
Yes. So that is our V curves. So that matches as well.
Yeah.
So now we have for the other systems like E upper U, which is grad U, which is that? You need to use this one.
Yeah. Yes. It's
It's x
x
hat
hat
plus y
y. Yes. Yes. X hat plus y.
and EV,
Just y hat.
obviously grad V. This is nothing but y hat. So E upper U would be x hat plus y hat. Which direction is that? This direction.
Yes. Yes.
And
Perpendicular to the.
yes, perpendicular to this line, this V curves, right? Sorry, U surfaces, perpendicular to the U surfaces. Okay, then what about the other one, EV?
Perpendicular to the.
This direction.
Yes.
Huh? See, these two angle between like this thing that is tangent to the U, like E upper U, like angle between this thing and this thing, which is this, so that is 90 degree. You see that?
Yeah.
Also, angle between, so let's erase those things. Angle between this thing and that thing, that is 90 degree as well graphically. You can see that here.
Yes.
Okay. and the final one, like the dot product, should give you like okay.
Yeah, it is obvious.
Well, you can see that E lower U and E upper U, they are not same vector, obviously. They are different vector, but if you take dot product, then it will give you 1.
Yeah,
So any vector at this point can be representation. Say let it be like A. This A vector can be expanded in terms of any kind of basis, either tangent basis or dual basis. Is that clear?
Yes.
Okay, great. So I think it's time to take a break. We are almost like you are there already. Any questions so far? So we have figured out 2 natural ways that are tied to the coordinate system itself to construct basis. Either you use coordinate curves and tangent to them, or you can use coordinate surfaces and gradient of them, or perpendicular to those. Is that comfortable enough?
Yeah.
Okay, so I can do a little more about it, but I think it's enough. It's enough to explain what's going on. It's enough to explain what's going on. I think let it be. Up to this point, it's totally fine. I need not to expand on this anymore. So if you understand this thing, we can actually change the notation and we can actually generalize this whole thing. So understand one thing. So transformation, when we change the coordinate, one of those things changes as a vector, as actually position vector changed. So the way position vector changed, when you change the coordinate, one of those changes like that. But another one, it's a kind of different species that we need to identify. So that's we are going to do next. Identify that gradient of V is basically, gradient of something is basically not a vector.
Yes.
Okay, so let's have a break for 5 minutes, and then we'll come back.
I have a question. Hello?
Hello. Sorry for being a little bit late. Had to use the washroom, so yeah. Oh, got something. Okay. Let's continue a little bit more here. I think it will be helpful. So say you have a vector a equals to 3x hat plus 2y hat. So how are you gonna express that in terms of this basis? So I want to write something into EU plus something into EV like that. Can you find those coefficients?
Yes.
Yeah.
How?
Dot product with EU upper
Yes,
and EV
yes.
upper.
Take dot product with this one and that one, and those will give you. So if you take E upper U dot A, what do you get? X hat plus Y hat and 3x hat plus 2y hat. What do you get?
5.
5. Great. And if you do this one, sorry, this one, what do you get?
2.
You get 2. So it will be 5 and 2, right?
Yeah.
So is that correct? If you substitute EU over there explicitly and EV over there explicitly, do you get correct answer?
Yeah.
Yes, 5 minus 2 is 3 and 2 is just 2. So yes, 3x hat plus 2y hat. So you can do that, right? Without much hurdle. So this kind of basis system, they may not be orthogonal, but they had a nice property that they were actually constant everywhere. So it did not change on position. But we could have systems like that, they change on position. So changes with position. So if you use a 2D polar coordinate on Cartesian plane, like flat space, so you have a relation between x and y to be x equals to, say, r cosine phi, y equals to r sine phi. So it's the relation between polar and Cartesian one, right? So what are the inverse relations are? So r equals to?
It's root over x square plus y square.
And phi equals to?
Tan inverse y by x.
Tan inverse y by x. So what are those EU? Sorry, like here we'll have like ER and E phi. What are those? So those are delta R by delta small r. Which is that?
Cosine phi I plus sine phi j.
Cosine phi x hat.
Sorry,
Cosine
x.
phi x hat plus sine phi y hat.
Yes.
So as you can see, it changes on position. So and E lower phi, what would be that?
It's yeah minus r sine.
R cosine phi y hat. Yeah. Can you see that, everyone? And what are those?
The gradient of r.
So what's that?
So it will be 2x, sorry, x divided by root over x square plus y square times.
Okay, it will be this. x hat y hat
divided by r.
square root of x square plus y square.
Yes.
If you take gradient of r, then you'll see this.
Yes. Yeah.
Which is basically in polar coordinate. You can write the same thing as cosine phi x hat plus sine phi y hat. If you transform everything into polar coordinate. What is this?
It's actually tough.
How tough is that? Can anyone tell me what's with this? Okay, let me tell you. It will be the same thing, but with a 1 over r. So 1 over r sine phi x hat plus 1 over r cosine phi y hat. It will be this. Okay, so let's explore some properties. So if you want to draw these vectors in different points, so let's draw these two things first. So in polar coordinate, here say radially outward vector is unitary 1, like in magnitude 1, but in this direction. Here again magnitude 1, but in other direction, like that. So it changes with angle, right? And what about the phi coordinate? So number 1, for r equals to 1, it will be unitary, that's fine, but it will change coordinate, change direction point to point. And if you go from the center, if you go further from the center, it will be scaled up, right?
Yeah.
Like that. So these are the basis vector that changes with position, right? You see that?
Yes. Yes.
So basically these are these define not just a single vector, they define vector field actually.
Yes.
Vectors at every point they define. So at this point, when you're talking about this point, you use the local tangent vectors of that point. So this will be your ER, and say this will be your E phi, like that. You expand any vector, some arbitrary vector v in terms of those bases. Or similarly, you can do with this one. So we haven't plotted those. You can plot those and you can use that. So you can think about this, that for each of the point you have a vector space, and that vector space has a basis of ER and E phi at that point.
Yes. Yes.
Okay, great. So this is stuff like you having a space on which each of the point you have a vector space. We call it tangent bundle, but it'll be clear why we call it a tangent bundle. It's basically we have a tangent space on each point. That's what it means. So
yes.
So sometimes when we work with position vector, it seems we are just working with one vector and we are moving that same vector everywhere. No, but point is we have a vector space at each of the point in space. Say you could have an electric field. Electric field at some point has its own vector space. So that's one point I want to stretch.
Yeah.
Okay, now it's time we actually sharpen our definitions and use much more mathematical way to describe same thing. And here you have noticed that we have had to use an external flat coordinate, flat space and corresponding Cartesian coordinate to describe that thing. So we do not want that. We want to put every coordinates on equal footing. So here, like Cartesian coordinate is kind of holy grail of us. We can extract many information out of it. We can understand it and we can deal with it, but not the other coordinates. So to expand anything in other coordinate, we actually went back to Cartesian every time. We do not want to do that. Is that clear?
Yeah.
I have a question. In this figure, several directions are shown. Are they the directions of those basis vectors ER, EPhi,
Yes. Yes.
and them?
So say this is your ER and this is your E5. Those are drawn different points. Here,
Okay.
this thing is your ER, this thing is your E5.
Okay, it means that in every point we will find some ER and EPhi.
No, yes, yes.
Well, the upper index and lower index has same direction here.
Yes, that's a specific case. When you have orthogonal coordinate, you'll have that.
Oh, okay.
Okay.
Okay, previously we also had that. This point we also had our EU, EV. This kind of thing.
Yeah.
But we were same for every point. That's why we did not realize.
For a Cartesian, actually they are basically same thing.
Yeah.
The dual basis look like the tangent basis in Cartesian.
Yes, in Cartesian coordinate, the tangent basis and dual basis, those are exactly same.
Yeah.
In any other coordinate, like obviously oblique coordinate, it's clear that those are not same. And also this kind of orthogonal but non-straight coordinates like spherical polar or cylindrical polar, 2D polar, this kind of coordinate, they have same direction because they are orthogonal, but they are not in same magnitude. So look, E phi and E upper phi, those are different actually. They have same direction, that's true, but they're different in magnitude. Okay, so it's time we sharpen our mathematical notion here in a more formal way.
Yes.
But remember that we did this kind of stuff here to understand things better, to have a better feeling that what's going on. Okay, so now let's clear the canvas. So again, we start with our discussion with the same thing we did earlier, the vectors. Again, it will give us more geometric meaning to the vector. So remember, we defined our position vectors like point in space. So this is say R1, this was say R2, and difference between those two were vectors, right? R2 minus R1. So we are extend that thing, but instead of specifying like R1 and R2 vectors, we are not calling those as vectors, but because we could have used non-Cartesian coordinates. So if you use non-Cartesian coordinates, then this point itself is not a vector, but the separation still is. Okay, so say you have a point here, let's call it A tilde, that's a point. Another point is B. Oops. B tilde. So these are 2 points. Separation between two points, we can draw an arrow like that, and that's going to be our vector V, and we call it vector AB typically, right? AB vector or AB bar, like that. So in this notation, it would be like R2 minus R1. We are extending that same thing like this. This vector is basically B point minus A point. We can do that, right? Because we had this thing in flat space, like in Cartesian coordinate. Hmm?
Yes.
Okay. So it'll be sharpened more actually when we, so we'll introduce vectors once again. So this is not the last step actually. Okay, so as we did last time, we actually constructed a curve that passes through these 2 points and tangent to that vector VAB, and parameterize that curve with some parameter, say lambda. Lambda equals to 0 was at A point, and lambda equals to say 1 at B point. We could actually write something else as well. So lambda equals to some lambda, lambda star at B point, lambda equals to lambda star. We could write like that as well. So if you do that, then for curve, on that curve, so point, arbitrary point on that curve at lambda equals to 0 is nothing but your A point. Where P is a point that lies on the curve.
Yes.
I think you
And
discussed this.
Yes, I discussed this thing. I said that I'm going to review it again.
Oh, okay.
So these 2 statements are true, right?
Yes.
Yeah.
Okay.
What does lambda star mean?
Lambda star is
Only
a
conjugate.
value of lambda at B point.
Oh, okay.
Lambda is a value of lambda when you have the point
Okay.
B.
Okay.
So instead of lambda, we can consider any.
Yes, you can consider sigma or anything.
Okay.
It doesn't matter what you're considering. So parameterizing is up to you. The way you want to parameterize, you parameterize it. So okay, so point at any point on the curve lambda is obviously, as lambda equals to 0 at A point, that starts at A obviously when lambda equals to 0, plus lambda minus
Lambda minus B minus lambda times B minus A.
Lambda
will that work?
lambda star plus 1
Lambda minus lambda star, yeah,
to B minus.
into
Okay.
B minus A. Is that correct?
Plus B.
No, I want my B to be automatically put a B over there, then it won't work. It won't work. So I think all I need is a divided by lambda star as well.
Yeah.
So if you have your lambda equals to lambda star, then it becomes 0, right? No, at lambda equals to lambda star, I want my B to be.
It has to be B.
Yeah. So previously I had like just lambda, and that lambda was 1. So I want this thing to be 1.
I think we should remove the minus lambda star.
Oh yes, lambda by lambda star, right?
Yeah.
Yes, this thing works.
Yeah.
So if you put lambda equals to 0, So this part it vanishes and you are having just A. And if you put lambda star, then A plus lambda star by lambda star, which is 1, B minus A. And that gives you B. So the same way, like we did tangent to the curve. So tangent to the curve is rate of change of point with respect to the parameter with respect to which the curve is parameterized. So that is basically this thing vanishes. You have 1 over lambda star B minus A, right?
Yes.
Now, if A and B are infinitesimally separated, then lambda star should go to 0, right?
Yeah.
So basically dp over d lambda, it gives me like limit lambda star tends to 0. That's all.
Yeah. Yeah.
Which is basically the definition of derivative itself, as we can see. So
Yeah.
you take two infinitesimally separated points and take a curve through this, have a parameterization on that, take the separation, divide it by the parameter separation, and take separation to be 0. It will give you the tangent vector to the curve, which in flat case we had b minus a. But now if you have any arbitrary coordinate system, then this b minus a, like in polar coordinate, like b minus a, it's a big separate. If it is a big separation, then it's a problem. But if it is an infinitesimal separation, it's always a vector.
Yes.
So now we have a precise definition for vector. Basically, MTW extends this thing like introducing derivatives, and I just showed derivative is justified. That's all. So now you have
yeah, I have a doubt. Like, yeah, I'm
Can you
clear
just
till that
repeat?
point. That yeah, I was asking like why we consider that derivative.
oh, why are you considering this derivative?
Yeah.
I mean, we already saw when lambda star equals to 1, that derivative gives us like b minus a, the separation vector that we already knew in flat space that happens to be a vector.
Actually, your voice was breaking in between. Can you just repeat that?
So okay, let's go to the fundamental thing. So we already knew that in flat space, in Cartesian coordinate, r2 minus r1 is a vector.
Yeah.
Is that clear to you?
Yeah.
Then we extended that concept to b minus a, like separation between 2 points, that to be a vector. But
Yes.
if you want this thing to be infinitesimally close to a, that will make things linear, right?
Yes.
So only way is to do that, like take b to tends to 0, like lambda star tends to 0.
Okay. Okay. Got it.
Just by taking that, it automatically produces the derivative.
Yeah. Got it.
Actually, I should have written this thing later. It'll like, yeah, it seems I was taking derivative. No. So basically, I wanted to evaluate this thing, b minus a divided by 1 over lambda, and take lambda to be 0. So take infinitesimally separated 2 points and divide it by the parameter, and that automatically gives me like dp lambda over d lambda.
clear now.
At lambda is equal to 0.
At lambda equals to 0, right? Yeah, I should have written that as well. So lambda equals to 0. So this is my definition of vector. We learned that last time, right?
Well, why such kind of definition is necessary? I do not get the point actually.
Okay. Okay. Really interesting question. Why it's necessary? So say you have a polar coordinate. Here you have like r1 phi 1, and at another point you have r2 phi 2. So obviously r1 phi 1, they do not add like a vector. Obviously those are not vectors.
Yeah.
This itself is not a vector. This itself is not a vector. Question is the separation between those two a vector? So can you do this thing, r2 minus r1 comma phi 2 minus phi 1?
Infinitesimal separation.
Answer is no and yes. No if they are not infinitesimally separated.
Yeah.
Yes if they are separated infinitesimally. Need a proof? Okay. Okay, let's proceed. Let's proceed and prove. So if they're infinitesimally separated, then this thing is going to be dr, and this thing is going to be d phi.
Yeah.
Yes.
Let's call it u. U equals to dr d, or we need actually two sets. This is one set. So let's call it dr1 phi 1 d phi 1, and another set v equals to dr2 d phi 2, like that. Infinitesimal separation.
Yeah.
So then you can actually add these two things. U plus v is obviously v plus u. You can do multiplication. If you multiply by m, that is nothing but just multiplying by the whole thing, like m dr1 m d phi 1, like that.
Yeah.
But and it'll never go off of the grid. That means you cannot have, as I proved earlier, like just adding two different phi can lead you to some phi that is not inside of your vector space. You cannot produce that because you are adding infinitesimal quantities. So infinitesimal coordinate change, that acts like a vector, that satisfies the properties of algebraic vector. Does it make sense?
Yes.
We'll go more rigorous than that. We'll see that partial derivative itself are vectors. You can add two partial derivatives. You can commute those two. You can multiply it by some number.
Actually, this is a new kind of philosophy for me right now. I didn't think about defining vectors in such a way.
Yeah, it might seem new, but that's the most natural way we can do on a curved space.
Okay, you may proceed, I think.
So any question like that? I actually want to stress this point a little bit more. I know it's hard for the beginners, but when it's comfortable, then everything else is easy. I also struggled with that.
So instead of uh, like I have a question about the above equation, like where we considered at any point p equals to a plus lambda by lambda star, right?
Mhm.
So instead of that, we can consider just lambda also.
Yes, if you have your lambda star like B, if your lambda star equals to 1, you have parameters such a way that your lambda star equals to 1, then you can just put just lambda.
So this is the general form.
This is more general form, yeah.
Okay.
You could have actually more general than this one as well. So you could write lambda equals to lambda 1, here lambda equals to lambda 2. You could do that as well.
Then this is fine.
No, no. Oh, what will be your p then? P at lambda, what will be it? So when it is lambda equals to lambda 1, it has to produce a, right?
Yes.
So how do you write like that?
Just p equals to a plus lambda.
Lambda by lambda 1, a. So if lambda equals to lambda 1, then it produces correctly. Plus, then lambda minus lambda 2, I believe. Is that correct? Lambda 2 divided by lambda 1 minus lambda 2, b minus a. Is this correct? When lambda 1 equals to lambda 1, lambda equals to lambda 1. Oh, okay. On the lambda, so I want here to be lambda 1 only. Lambda 1. So then it vanishes. And the bottom I need 2 minus lambda 1, I think. I think this one is correct.
Yeah, this is correct.
This thing is correct. Yeah. So if your lambda equals to lambda 1, then this part vanishes. This gives you a. That's correct. Then if you have your lambda equals to lambda 2, then this thing produces lambda. No. We need more actually, right?
We actually don't need the lambda by lambda 1 before a, I think.
It's just a.
Yeah, that should work.
Yes, you're correct. Yeah, this works. Yeah, you can put your like lambda equals to lambda 2, and it gives you like this thing 1. So like, yeah, it gives you b. So now you take separation between infinitesimal, like make your lambda 2 goes to lambda 1. So that will give you like infinitesimal separation between those 2 points. So this thing, b separation between point, which is may not be a vector, divide by a number lambda 2 minus lambda 1, which is just a number, it's not a problem. So take limit lambda 2 tends to lambda 1. So then b minus a is just infinitesimally separated, like if you make that, and that gives you like, it's a vector, legitimate vector, and also by definition it's dp d lambda as well.
What is lambda 1 and lambda 2 in the figure?
Lambda 1 and lambda 2 are just parameter values at 2 different points. So this is going to be like dp lambda over d lambda at lambda equals to lambda 1. that's it's gonna be.
Well, how do we define the length or some other things from this definition?
No, we do not define that. We do not know what the norm of V is.
Oh, okay. But the direction is from A to B, something like that.
Yes, tangent to the curve. Direction is tangent to the curve, and the scaling, it depends on the parameterization.
Yeah.
So is that clear to everyone that this thing is a legitimate vector?
Yes.
Okay. Actually, we'll go deeper than this. It's just the starting. MTW itself.
Yeah. I think it is actually it is a legitimate vector because this actually tangent to lambda is equal to lambda 1. It is tangent to lambda is equal to lambda 1. Isn't it?
Yes. It's tangent to the curve. It's a tangent vector. That's why it's a legitimate vector. You can. Yeah. But many physicists actually think this way, like separation between 2 points is a vector. It's a bilocal object.
Yeah.
Mathematicians won't like that. Yeah, but many physicists will like it. Okay.
I'm quite confused about one thing, that in the figure we found that a point called lambda star. Okay, so I want to know that in the curve we found the lambda star. Okay.
No. Probably you missed a little bit. So point is, Pooja was asking like, what if I can more generalize it? So then I said like, okay, you can tell like your A point is at lambda equals to lambda 1 and B point is lambda equals to lambda 2 point.
Oh.
Then this thing happened.
Okay. I am.
Then you discard this one.
Okay, now I understand.
Okay, so point is to make a vector, you need a derivative, because derivative has those nice linear properties. So we can show that actually diagrammatically. So say in polar coordinate, if you have a point here, which is r1 phi 1, and another point like here, they're separated by big amount, r2 phi 2, then if you add those like vectors, then what do you get? So r1 plus r2 will be a big thing, right? So this distance plus that distance, how much would be that? Probably like here somewhere. And phi 1 plus phi 2 would be like, it'll produce like this one.
Which distance you are talking about?
So this one, this thing. So this is r1 plus r2.
Oh.
And this angle is now your phi 1 plus phi 2.
Yes.
Obviously, it's not a vector. It doesn't satisfy those properties.
Yeah.
But what if it's infinitesimal? What if those are infinitesimal? So say we were at this point and you had dr1 and d phi 1. So dr1 is probably a little bit in this direction and d phi 1 is a little bit this direction. So effectively, probably we'll have this one, infinitesimal one. And at the same point, if you have another infinitesimal vector, that is probably this one, so they will have all the nice properties like you could construct a parallelogram and say this is my the resultant vector like that. I think it'll take some time to absorb this idea, but we'll generalize this actually.
Yeah, it seems everything is really infinitesimal.
Yeah, everything is really infinitesimal, then it works, yeah. But if it is infinitesimal and you divide it by some another infinitesimal quantity,
Yeah.
which is a number actually, then the result is not an infinite, but whole thing is a vector, right?
Yeah, yeah.
Yes.
That's why we are talking about derivatives.
So vector is a derivative. Okay.
Yes, vector is basically a derivative, or other way, derivatives are vectors.
Yeah. That's nice.
Okay, so now we already saw how to expand these things in terms of our defined basis. So for an arbitrary curve, as you had like dp over d lambda to be some vector v, here we expanded like this. You remember from last class that delta p over delta x mu dx mu over d lambda, like that.
Yeah.
Which is basically the form of tangent vector. So this is we called our basis for obvious reason, like as we did today. This is nothing but delta r over delta x mu. We call it e mu, and these are our components x mu dots. We call it v mu. So you can expand any vector, like you can have a parameterization such a way you can express any vector this way. So probably you're confused about like how to measure these things. We'll see. Bit by bit it will be clear. It will take some time, but trust me, it will be clear. We're just constructing formalism, so it will take some time. Okay, next thing is a definition, basically. Definition of two things together. So let's consider you have your space. It doesn't need to be flat or anything. It could be any space. And say you have your coordinates like x1, x2, x3. Those are not Cartesian coordinate, and those need not to be Cartesian coordinates. So, and you have a scalar field f, which is a function of those coordinates x1, x2 up to xn. Usually we talk about 3. Then these are the coordinates. That's nice, but we could call it a point at like f at some point p. We could call that as well. So say at this point, the name of that point is p naught, and f is has a value at that point, f at p naught. Even before setting up the coordinate, we could have that, right? When we set up the coordinate, we'll have this expression. Are you guys confused at this point? Okay, no. Okay. Let me simplify this thing. So basically, what we're having, say you have a room and you have a temperature distribution everywhere. So you haven't set up a coordinate yet, you're not measuring distance and anything else, but you still can have a thermometer and put different points and have different readings, right?
Yeah.
So now you go to a point P naught and you have a reading F at P naught.
Yes.
Yeah.
Now you go to an infinitesimally separated point, some P, which is infinitesimally separated from P naught. You go to a point P and you have a reading F at P. Question is, can you expand your F at P in terms of F at, like, things at P naught? So if you do that,
Taylor.
Yeah, Taylor expansion. So you can write approximately like this. Actually, let's write exactly first. So F at P, and you could write like plus separation between those two, right?
Yeah.
Yes.
So plus delta F. Delta F between, like, say, P naught and P.
P minus P naught into.
Yeah, separation between P and P naught. That's what I said. So
Yeah.
now I want my delta F to be expanded. So to do an expansion, I set up a coordinate. Now I set up it need not to be a Cartesian, it can be any parameter, any coordinate system. Just the coordinate means, as I said, it's a bunch of numbers. So numbers put onto space. So that's what I do. Then how do I write at, like, this delta F? So basically, this F at P naught, that's fine. Then delta F is basically F at x mu, like the coordinate values, at point P minus F at coordinate values at P naught. Is that correct?
Yes. Yeah.
So let's call two things, like coordinates at P naught. Let's call those x01, x02, like x01, x02, x2 naught, x3 naught, like that, up to xn naught. And coordinate values at this point is obviously x1, x2, and x3 up to xn. We can do that. So what I can write is, let's erase this. I can write like this: if at P naught plus, here x mu at P is just x mu, right? Like x1, x2 up to xn. So I just write like this: if at x1, x2 up to xn, like that. Then minus if x1 naught, x2 naught up to xn naught.
Well, I have a question. Is f of P naught is equal to f of x naught 1, x naught 2, x naught n?
Sorry?
Is the f of P naught is equal to f of x naught 1, x naught 2?
No. X mu at P naught, like coordinate values at P naught is x10, x2 naught, x3 naught up to xn naught.
Well, what is the difference of okay.
What's the difference of?
What is the difference of f of P naught and f of x at p naught.
F of
X mu at p naught.
Okay. So it's an abuse of notation, I would say. It's an abuse of notation, but physicists usually do that. Those are same thing. So
Yeah.
here, f at p equals to f at x mu at p. So
Yeah,
yeah,
that's what I was asking actually.
yeah, mathematician would not like it. We do it a lot. So what we mean here, actually, we mean that f represents some physical quantity. That physical quantity's point p is the same as you evaluate the coordinate at point p and evaluate the physical quantity at that coordinate. Those are actually the same thing. That's what we mean, but mathematician won't like that.
Well, I'm an engineer, so
Why?
no problem.
I mean, why won't mathematician like that?
Because this thing. Say you have a function. Say f of x. Say if you have a function f of x equals to x squared, and then say x equals to say t squared. Here we are trying to write f at t equals to f at x at t, which are not same thing mathematically. So if you want to write f at t, by this definition, f at t would be like t squared. And if you want to write this, then you have to use this definition. So f at x is x squared, then x of t is t squared. So it will be like t to the power 4. Those are not same.
Yeah, these are not same.
Yeah, but as long as we understand and do not confuse, then it's fine. We are not going to confuse this kind of situation. We will understand, okay, we have to, like when we write this, we understand, okay, that's basically means you just evaluate that, like you found the variable at point P, nothing else.
Okay.
Okay, so how do I write this thing in terms of this coordinate separation? So I can do the same trick I did when I derived those chain rule, remember? I add and subtract same terms many times, like add and subtract, do this thing. So let's do this thing. So if at x1, x2 up to xn minus if at just change one of the coordinates. So x not 1 and then leave the other fixed.
Okay.
You see where we are going?
Yeah. Yes, it's the partial derivative terms.
Yeah, we'll introduce this partial derivatives here actually. Yeah. So then you have to add the same term again. If at x not 1, x2 up to xn, then subtract this term, that x not 1, x not 2, and then up to xn. Then you just proceed doing the same thing over and over again, and then last term would be your f x naught x2 up to x naught n, and just before the last term you'll have like plus f at x naught 1, x naught 2 up to xn. Agreed?
Yes.
So the first two terms can be written as like this: f at p naught plus delta f by delta x1, delta x1, right? The first one.
Yeah.
Then you have this thing, this thing. So that the pattern continues up to delta f by delta x n delta xn. Is that correct?
Yes.
Okay, great, great.
If we don't consider the delta x1 is infinitesimal, then there is some second order, third order term.
No. We haven't considered like yeah. There. Oh, okay. So yes, it's approximately equal to.
Yeah, not equal.
Not equal, but when you take the limit, p tends to p naught, then it's equal, right?
Yes.
Okay. So now, what is delta x1? Delta x1 is the value of x1 evaluated at p naught, p minus evaluated at p naught, right?
Yeah.
So what we can write, if p naught plus delta f by delta x1, this thing we write x1 evaluated at p minus evaluated at p naught, like that. Sorry. X1 at p minus x1 at p naught. And the pattern continues, so we just write mu instead of writing those all things down. Sum over mu. Is that clear?
Yeah.
Okay. Okay. So then this thing, like the coordinate separation between those 2 points, we define a new thing. Okay. So coordinate separation between these two things, we define an angle bracket dx mu comma p minus p naught. So this is the definition of like this angle bracket and dx mu.
Yes.
Okay. So what we can do is take okay, there are several things to consider. Number one, I can take delta f over delta x mu inside of this thing, like I can multiply. Actually, no. I should write another step to explain this thing. I should write another step. Okay, let's not write this thing right away. Let's not write this. So, okay, so this is basically the same situation we started with, right? This is basically the same situation we started with.
Yes.
This is basically some number at p equals to some, like that number at p naught plus change in that. So that is basically our delta x term, right? So delta x1 equals to, like, delta x mu equals to this thing. So this is basically the same thing we started with.
Yeah.
Okay, so instead of defining here at this step, we define the same thing at the previous step. Let's see that those things, like the definition is consistent, that we need to prove actually. Okay, if we defined, like, just leave it there, then at this step actually, instead of defining new coordinate, like when we had like f at p minus f at p naught, define those angle brackets such a way, we'll see that those are actually same thing, like it's consistent. That's we're actually trying to prove. So f at p naught plus this angle bracket df p minus p naught. Why we're trying to write like that? Plus higher order terms. Okay, what does it mean? P minus p naught is a vector, right?
Yes.
Yes. So basically, we already know from our elementary calculus that if at p, if at some r, when we had Cartesian like coordinate, we had f at r naught plus gradient of f dot.
Is this inner product?
No, it's not inner product. It's a generalization of that.
Okay.
So it's not inner product. It's something else.
Okay.
A little bit different, but it's almost inner product. We only claim few properties that it has linearity. That's all.
Okay.
We are trying to extend this. So basically, we knew this thing already. R minus R naught plus order of 2.
Yeah.
So we actually had to define some angle bracket that carries the same properties. Same properties like grad f dot, this part. This is not inner product. Remember, we call it piercing. There are meaning. We'll see it later in a moment actually. Okay, so if we do that, is it consistent? That's the question. If linearity is held or not. So if we do that, then at this step, what we can write? We are trying to identify two things, like what is df and what is this angle bracket, right? Yeah, we want to understand those. So what we can write is f at p naught, that's fine. Then plus sum over mu delta f by delta x mu. Then x mu minus x mu at p naught. How we can write? So x mu would be like x mu at p naught plus something, right? Like x mu at p by this definition would be x mu at p naught plus dx mu p minus p naught, right?
Yeah.
Define that like that. So obviously we can use that thing at this point. So that will give us dx mu p minus p naught plus higher order terms. Like, so now as we claim that this thing is linear, so this becomes like this line is continues over here. It gives me, so you take this sum inside of this angle bracket, it gives you delta f over delta x mu dx mu comma p minus p naught. So it can, this thing can be held. like this thing, this is linear if and only if this term is equal to that term, right? Then it's correct.
Yeah.
So number one, we have a definition of df in terms of coordinates. Df is nothing but delta f over delta x mu dx mu, and which we identify as a natural generalization of our previous df equals to delta f by delta f mu dx mu, the multivariable chain rule. It's a natural generalization of multivariable chain rule. That's one thing. Another thing is considering this thing to be linear, we found how to take this gradient, like the separation of something like df, and pierce with the separation between the infinitesimally separated points. Those are basically vectors.
Okay.
Okay. Now, again, we can the separation between P and P naught. Separation between P and P naught. These two points can be parameterized by a curve, and considering like lambda equals to 0 and lambda equals to 1, this is going to be our tangent vector v, right? P minus P naught, right? This is going to be our tangent vector v. Also, yeah, obviously multiplied by d lambda, right? Yeah. This is going to be our v d lambda. Like dp over d lambda equals to v. So p minus p naught, when those are infinitesimally separated, it is v d lambda, right?
Yeah.
So we can substitute that. And definition is consistent so far. So f at p equals to f at p naught plus df, which is basically a natural generalization of infinitesimal separation of f multiplied by v dt.
D lambda.
Lambda, sorry. Plus higher order terms. Like that. So, as we have claimed that this angle bracket is linear, this thing is true as well. Order of lambda squared. So now we need a relation between df over d lambda and this term. So that's the final thing we need to stick to. So as that's infinitesimally parameterized by small lambda, so we can evaluate df over d lambda as well. Right? So this is limit delta lambda tends to 0 if at p minus f at p naught divided by delta lambda, right?
Yes.
This is by definition already. So, and substitute this thing like expansion of f at p, we get limit delta lambda tends to 0 over delta lambda So the leading term, like if you substitute this whole thing over here, then leading term like f at p naught, that cancel out. We are left with only the only this term, that is this thing, d lambda or delta lambda I should write actually, as I am considering taking limit later. So yeah, delta lambda I should write. Okay, and also higher order term, that when delta lambda taken to be 0, those goes away, so we do not worry about. So that is basically this thing.
Yes.
Okay. Okay, then what we have learned so far. So see this thing df over d lambda, we already knew that df over d lambda is linear in component of its tangent vector. Remember, we wrote like this, df over d lambda equals to delta f over delta x mu dx mu over d lambda, like that.
Yes.
Yeah. And x mu dot, those are component of vectors, right? So we could write basically like v mu delta f over delta x mu.
Yeah.
So what's the addition here? What's the addition here? So here we need not to worry about a coordinate. Here we considered a specific coordinate and got this result. Here the full vector, like the derivative is linear in full vector, not just components. So it's a geometric generalization of this statement only. But we had to introduce new notation, that's all. We had to define that angle bracket cleverly. Right?
Yes.
So with this definition of angle bracket, we can construct our algebra here. So what is d of something, we'll call in a moment. Can I take 10 more minutes today? I'm actually done for this segment almost.
Sure.
Yeah.
Okay.
Okay, so with this clever definition of angle bracket, we got several things. One is generalization of this thing, just df. It generalizes to this df. In MTW, you'll see a boldface notation. So basically, without boldface and with boldface are same df, but here we understand it much more rigorously. This object, it can take input a vector. See, like we have written as angle bracket. So this df can take input as a vector and produce the directional derivative. So which object we knew in our elementary calculus that can do that? Take a vector and produce the directional derivative in that direction of vector.
It's gradient times dot product that vector.
Yes. So when we did that, grad f dot v, that was actually delta f df over d lambda, right? In elementary calculus, remember?
Yes.
So it's understood that grad f dot this part up to this part, this is basically df. So the new name is still gradient. We call it gradient. We call it gradient. But this is basically this df, separate infinitesimal separation vector. But why it's a gradient, like it's a full object? It's a full object means it's still infinitesimal. Full object means it's not component. That's what I mean. So it's a full object, like as the gradient, because df it has all the information of how f changes in every direction. So if you, as we saw in this derivation earlier, that you can expand like df equals to delta f over delta x mu, dx mu. You can call this dx mu as your basis, and then delta f over delta x mu are your rate of change in a particular direction, how much that f changes, right? So it's a really natural generalization. So our very old infinitesimal change in f had all information already. So when we say infinitesimal change in f, do we say which direction you taking this separation? No, we are taking this separation in arbitrary direction. So that arbitrariness has to be embedded inside of it. When you provide a direction, it tells, okay, in that particular direction, rate of change is this. But when you do not, then it's a still general object. So this is our gradient.
Yeah.
Gradient. And we have defined the new basis. We can define our new basis system like dx mu. We call it dx mu to be omega mu from now on. Lower bar omega mu. Okay. So this omega mu are infinitesimal, remember? But it doesn't matter infinitesimal or finite, because when I write x hat, is it infinitesimal or is it finite, or is it something like you can
It's
put
finite.
it?
It's finite.
How do you know it's finite?
X had unit vector, so
Oh, okay. It has a magnitude of unitary, right?
yes.
Okay, yeah, you can say that in terms of when you have like metric tensor defined, you know how to take this dot product with itself. Then you can tell that.
Yeah.
But before that, it's just a symbol. It tells you like walk in the right hand direction. That's what it says. Right? It's just a tag. It tells you like, okay, you need to go this way. Okay, let me give you an example. So when you wrote like 2x hat plus 3y hat says gradient of some f has this value. So it means your f has a rate of change 2 in x direction and 3 in y direction. The same information is over here as well. 2 dx plus 3 dy. In x direction, rate of change is 2. In y direction, rate of change is 3.
Yeah. Yes.
So I can use this thing as basis, but yes, these bases are infinitesimal bases. So, but it doesn't matter our bases are infinitesimal or not. As long as we know how to do algebra with it, it's fine. Okay, so this is one generalization, generalization of gradient, and that always we had with our elementary calculus, like infinitesimal change in f, that already had that. Okay, then linearity with vectors. In Cartesian coordinate, when we did that, it was really apparent, like grad f dot v was df over d lambda. Okay, now we need to do several things that that will help us to understand the algebra more. So what we have done is df over d lambda equals to the definition, with the definition of angle bracket, df comma what, v, right?
Yes.
So what is v? dp over d lambda, right?
Yeah.
V is nothing but dp over d lambda. Okay, now instead of using f and lambda, what if we use some coordinates? What if we use df over dx mu, like this thing? Instead of lambda, we use one of those coordinates as parameters. What happens then?
If the coordinates are linearly independent, then there is only one.
For God's sake, just change lambda to x mu. What happens?
If I change lambda to x mu, then the other term will be 0. Like
no, this will be this.
Yeah. Okay.
Huh?
Yes.
Is there any confusion with that? Like we chose one of those lambda to be one coordinate curves. That's it. One of those coordinate curves, say x1. So then delta p over delta x mu, which was a tangent basis, right? It gives us df comma e mu. So if you have a gradient df, you pierce, we call it piercing, you pierce with e mu, it gives you delta f over delta x mu, the components of gradient.
Yeah.
In other words, so here you can see, so if you have a vector, that vector is represented as a derivative with respect to some parameter, you just take derivative of that function with respect to that parameter. That's what it is. Okay, then if we do the other way, dx mu over d lambda, what's that? Using this relation and linearity, that's all.
I can just replace x mu. Replace the position of
dx mu, yeah, right.
And dx mu d lambda.
Dx mu, no, here dx mu, that dp over d lambda, which is v, right?
Yes.
And we already know dx mu over d lambda is basically components of v, so which is basically v mu we have written. Yeah. We'll summarize the result. So we get this. What if we chose both f and lambda to be some coordinates? So delta x mu over delta x nu, what happens then? Obviously dx mu comma
0.
Delta x nu, delta p over delta x nu, what's that? Delta p over delta x nu, what's that? It's e nu, right?
Yeah.
And this thing is nothing but, we already know, this Kronecker delta.
Yeah.
So you can think even this very definition, like this thing as the definition of angle bracket itself.
How did it become e nu in the last question?
No, yeah, because if you substitute like over there, then F becomes like mu and lambda becomes nu, right? Delta P over delta nu is E nu, right?
Okay.
Let me write one more step. So delta P over delta X nu.
Okay.
Okay. So now we are ready to summarize the result. So basically we have several definitions. First, we have definition like tangent basis or vector basis, we are going to call it. Vector basis E mu are defined to be, let me summarize it because otherwise we have to do it again. I do not want to do it again. So yes, that's one definition. We understand that, what it means, right? How much the point changes when we move from one point to another in the direction of one of those coordinates, x mu. So this is basically tangent basis. And corresponding, the dual basis here is basically dx mu, right? Because in this relation we see those are dual.
Yeah. Yes.
So we call it omega mu. The angle bracket is defined to be, oh no, a vector say v can be written as in terms of those bases v mu e mu.
Is this angle bracket is some kind of mapping? Or
Yes, you can call it as a map. It's a map from a, it takes a vector as an input and produces a number.
yes.
Map from a vector to a directional derivative.
Okay.
Okay. Now you have your omega mu's and you can add those things like say a mu omega mu. You can sum those things up. It will give you something, right? Some a, but that a is not going to be a vector, obviously. It's going to be something else because they have different bases, not vector basis. They have gradient as basis.